So, knowing the 3D geometry of a scene like this is really useful for tasks in robotics. Consider, for example, a robot approaching this table of objects, which may want to plan a path to clear these items away or to place new items on this surface. The 3D geometry is great for this, and there are many fantastic algorithms for finding this geometry, using multiple RGB or depth images to form a sparse or volumetric reconstruction. However, these all tend to make this fundamental, critical, multi-view assumption that you are able to move the camera around the objects in the scene and observe them from all directions. In many cases, that motion isn't possible. A robot approaching the surface may wish to start clearing these items away without having to move all the way around to see that geometry. From a single connect image, we can see how little information the sensor actually views of these objects in one frame due to occlusions. And this motivates our work, where we set out to recover the dense 3D geometry of the scene, but using only a single depth image as input. In effect, we strive to predict the output of a Connect Fusion system, but with just one depth image instead of a whole video. Of course, you could use a database of 3D models to complete the geometry, but you can't do that if you've never seen these objects before. Another brittle approach is symmetry. If the axis of symmetry is misestimated or cannot be found, then the predictions can be catastrophically wrong. Last year at CVPR, ShapeNet did focus on reconstructing this missing data, but only for single objects and with class labels given. Our system is designed for multiple objects of unknown classes in clutter. Zeng et al. Directly tackled our problem, using the observation that man-made objects tend to be convex. Their heuristic segments the scene, before the voxels in each segment are marked as occupied if they land within its convex hull. And there are other methods too. Finally, in our work, we are inspired by previous segmentation work, which makes the observation that shape transcends semantic boundaries. In our man-made world, at a part level, there is a lot of repetition between the shapes of objects. And we exploit this to learn from a set of training examples how to complete previously unseen objects and scenes. So let's have a look at our method, using this toy example. Here's a simple scene. And here we can see a horizontal slice through the scene, represented as a voxel grid. We're seeing the ground truth here, with occupied voxels in red and empty voxels in white. And here, a Connect has viewed this voxel grid from the bottom. When the Connect sees the scene, it only sees this outer shell as being occupied. All the voxels behind the first observed surface are of unknown state, and we represent these as grey here. We make the observation that a single point on a depth image, the shape in the neighbourhood of that point is very informative about the occupancy in its neighbourhood. And we use this to map from points on our depth image to a prediction of scene geometry in a 3D region around that point. So, at test time, we select a point at random from our depth image, and we compute a feature vector for our query point. And this is composed of samples of a geometry in its neighbourhood. We then map this feature vector to a prediction of geometry in the neighbourhood around this query point. To do this, we use a structured random forest. Our featured representation of a point is passed through the forest and mapped to a multidimensional prediction of voxel occupancy. This cuboid voxel geometry prediction is then transformed into world coordinates, centered on the query point and aligned with its surface normal. So, at test time, we've selected a point on our depth image, we've computed a feature vector, and we've mapped this to a cuboid prediction of occupancy. And this is then placed in the global coordinate frame. So now we've made that prediction, we can choose a new sample point, and into a cuboid around that point, place a new prediction of occupancy. All our predictions are then accumulated into the prediction grid. We average their truncated sign distance function representations in this step, but we also make sure that predictions respect the observed geometry, And you can come and see our poster for some details on this. So that's how our method works in 2D. Now let's see it again in 3D. Here we have a test scene, and here's the depth image captured by the connect. Just as in 2D, we sample a single query point from the depth image, and we use that to look up a prediction of geometry. This is then inserted into the scene. Notice that in 3D there's an unconstrained degree of freedom when aligning this cuboid with the surface normal. To account for this, we align the cuboids in 3D so that their top and bottom faces are coplanar with the world's ground plane. So this process continues, another point is sampled, and another prediction is made. It's the aggregation of hundreds of these predictions which is used to complete whole scenes. Two tricks that make this work are shown here. Crucially, our predictions and our features are reasonably invariant to the position of the camera viewing the scene. We also found that performing machine learning on the TSDF representations gave improvements above binary occupancy values. Now, to train and evaluate this system, we needed data where the camera had viewed the front and backs of all objects. So I started a quest to find this sort of data, and I started a website which catalogued existing RGBD datasets, which I actively maintain, so you can look it up. There are loads of datasets here. And these are great datasets for our researchers to use, but none of them had what we needed, which is scenes where the camera had viewed every part of visible surface geometry. This is essential for training and evaluating our model, and it just didn't exist. So we captured our own dataset of scenes, where we took pains to capture this full surface geometry. So now for any depth image input, we can compute the ground truth occupancy aligned to that viewpoint. We define a train test split on this dataset, ensuring no overlap of objects or capture locations between the splits. So now let's see some results. On the top left, we have an input RGB view, which we don't use in our algorithm. On the right is that 3D information captured by the connect, and you can see the missing geometry here. This is the input to our algorithm. On the bottom right is our prediction of geometry, and note that we've inserted the ground plane here for visualization. And for comparison, on the bottom left is the ground truth geometry as computed by Connect Fusion. You can see here that we do a good job of completing the shapes and the bulk of these objects in the scene, which for a robotics application gives far more useful geometry than what the Connect saw in just one depth image. Here's a comparison to a baseline. We give the baselines access to a ground truth segmentation of the scene, and yet you can still see how it underpredicts in many regions. And here's another scene where again we're completing the shape and the mass of these foreground and these partially occluded background objects. And here's another comparison to the baseline. Now, because we've got this ground truth occupancy values, we can quantitatively evaluate our system. We evaluate over all voxels which are inside the camera frustum, and which are also inside the extents of the room, and finally, which are behind the depth image, as viewed by the Connect. So this is our evaluation region here. You can see here that even though these baseline methods have access to the ground truth scene segmentation, we beat them on intersection over union and recalled scores. So we designed this system for tabletop scenes, but we wanted to see how it would do on a room level dataset, like NYU. It's a great dataset, but unfortunately it doesn't come with this ground truth occupancy for training or testing a room scale version of our algorithm. However, researchers have previously painstakingly recreated it in synthetic form. It is a somewhat crude representation of the real world, but we were able to use it to train a room scale version of our algorithm, which we could then use to test on the real NYU dataset. So while our system's designed for tabletop scenes, we still managed to do a good job here. Here's our prediction on the bottom right. We give an idea of where there's gaps behind furniture that we could safely navigate into. And here's a bath where we're predicting some of this missing geometry inside this bath. We've also got a quantitative evaluation on the synthetic NYU dataset, and this is in the paper. So now let's revisit our original aim. We wanted to predict occupancy from a single depth image. On the top we see our input data, just as before, and on the bottom right our prediction, which has been made just from this single frame. On the bottom left we have the output of Connect Fusion, which is currently just completed from the one frame. We're now going to move the input camera, and you can see that Connect Fusion gets more and more data to fuse into it. But it takes a long time before it starts to catch up with our completion, which was made from just the first frame in this sequence. And now let's go back to this kitchen scene we saw at the start, which is from the NYU dataset. We saw how little data there is present in the Connect image. And we've got now our completion from our model trained on our tabletop dataset. It works well, but it also shows a limitation. Where there's a large amount of missing data, like on this glass coffee machine, we can fail to form completions. One interesting area for future work would be to be able to make use of multiple frames as input, instead of our single frame. So new data could replace our predictions as they arrive. And since we created our dataset, there have been new datasets released, also with full geometry. And this large dataset only captures single objects compared to our scenes, but it's of a larger scale and could help improve reconstruction quality. So that's how we completed scenes from a single depth image. We've got code and data available. Please come and see our poster. Thank you.